Right, let's continue doing some of the exercises in the study guide. Right here we have problem 20 and it says to express the confidence interval in the form of plus or minus c. So right here, what we have right here is that we have, let me see, let me get a pen. So we have the proportion of a population, and that proportion is being estimated that it falls between two values, a negative 0.061 and 0.579, between 6% and 60%. So now, how this proportion of the population was estimated? Well, typically it is from the proportion in a sample minus a number, what is called the margin of error, the proportion in the sample plus the margin of error. This margin of error for proportions is given by the z-value square root of pq over n. Right, but let's right here, what we want to know is what is this p minus p plus e. Well, if this quantity is equal to this value, what we have is that the proportion in the sample minus the margin of error is equal to the first number, which is negative 0.061. Is that a negative? It shouldn't be a negative, but oh yeah, okay. And this number is equivalent to that, so p plus e would be equal to 0.579. When we add these two numbers, we get the two p hats, the two proportions of the samples is equal to the sum of these two numbers, which is 0.579 minus 0.061, and that gives me 0.518. So divided by 2, we get that this is 0.259. All right, 0.259. Once we have it 0.259, which is two answers, we have it three answers, have the 2.9. We need to find e. So we can use one of these equations. For example, let's use that p hat plus e is equal to 0.579. We know that p hat is 0.259 plus the margin of error is equal to 0.579. So e is equal, this which is positive, let's subtract that quantity from both sides. And we get that the value of e is 2.59 negative cancels, so 2.59 0.579. But yeah, 2.01. Oh, this is 0.2, sorry. Oh my gosh, my eraser. Okay. So right here, this is 0.259 negative. When I subtract these two, is 0.2. Right, so I get 0.32. So this is 0.32 plus or minus. So that would be this answer right here. Okay. So again, just to comment on this problem is the idea right here is to take an interval that is already simplified and break it down into the pieces that made the interval, which is the proportion of the sample plus or minus the margin of error. Okay. All right, let's do our next problem. So let me leave this thing. Maybe we did it too much. All right, let's look at problem 21. And in problem 21, now we have a confidence interval for the proportion of a population written in the form of plus or minus. So 0.307 plus or minus 0.058. Well, this right here is the proportion in the sample, and this is the error, the elasticity of that interval, to be able to estimate the proportion of the population at some level of confidence, which we're going to do later. So then the proportion of the population is estimated to be the proportion in the sample minus the margin of error, which is 0.058, the proportion in the sample 0.307, plus the margin of error, which is 0.058. So let's add these numbers. 0.307 plus 0.058. So the upper limit is 0.365, and the lower limit is 0.307 minus 0.058. That gives me 0.249. All right. So what this is saying is that the proportion of the population is probably between 25% and 37%. So we got, this answer is number, see a bit, I think 2.49. Okay, so that's correct. All right, let's move on. All right, so let's skip a few problems and let's do 24. So in number 24, says assume that the sample is used to estimate the population proportion P. Find the margin of error that corresponds. Okay, so right here they're asking for the margin of error. So remember that we estimate in number 24, and the rest are the same. We estimate the proportion of a population by calculating the proportion in the sample minus the error, and taking the proportion in the samples and adding the margin of error. Now, in this particular case, we took or questioned or surveyed 470 individuals. Out of those 470 individuals, 50 said yes to something, right? Agree or answer are the proportion who are correspond to the study that we're doing. So the proportion in the sample is going to be 50 divided by 470, which is 50 divided by 470. That gives me 0.106. Okay, let's use one more decimals. So that is the proportion in the sample. Okay, now that's good to know. Now the margin of error in this case, we may not need that value. So the margin of error in this case is the z-value times standard deviation. Standard deviation for proportions is the standard deviation of the population. In this case, we use the sample times q divided by n. All right. Now, so the error is going to be the z-value that corresponds to 95% confidence. We know, we did that in a video already. That value is 1.96. That comes from the C tables. Square root of P, which is, disappear. P, which is square root P, which is 0.1064 times Q, which is 1 minus P. So that is 0.8936 divided by the sample size, which is 470. Right, so that is the E. In this particular case, we didn't need to calculate the proportion of the sample, but just in case we need it. So let's do this calculation. So 0.1064 times 0.8936 divided by 470. And then we take the square root of that and multiply that by 1.96. We'll get 0.0. So I get 0.027879. Okay, so that's what we get. Okay, so let's look at the next problem. So this was number 24. What changes in the next problem? In the next problem, we have that the sample size is 430. Of that sample, this is assume that this is the people who agree with some policy, and so 80 agree with the policy. So that's the proportion of the sample that agree with the policy. We are creating a 90% confidence interval. What will be the margin of error? So the margin of error, we have the formula right here. So let's now we're doing 25. So in number 25, all right, we are just going to calculate the margin of error. So this is our formula right here. All right, so let's begin with a different kind of calculation. In this case, let's start with the z-value. Okay, so what is the z-value? Since we are creating a 90% confidence interval, we know that the z-value for 90% confidence is 1.645. So this z-value is 1.645. Again, we calculated that earlier. The proportion in the sample is going to be 80 divided by 430, which is 80 divided by 430. 80 divided by 430 is equal to 0.186. Q, which is 1 minus P. I don't know why my things disappears when I let me see. 1 minute. Let's do these calculations again because this is very sensitive tablet. So 80 divided by 430 is equal to 0.186. 0.186. So Q, which is 1 minus P, will be 0.8139, 0.814, right? So we have everything that we need. So the E for problem number 25 is 1.645 times the square root of 0.186 times 0.814, everything inside the radical, divided by the sample size, which is 430. Let's calculate that number. Divided by 430, and then taking the square roots. Let me see, 0.186 times 0.814 divided by 430, the square root of that, times 1.645, I got 0.03086, 0.0309. All right, so right here we have this answer. Okay, so again we get the idea. And for problem 26, let me just set up the problem so we can get to more other exercises. But in problem 26, what changes? Still we're trying to calculate the error, and the confidence interval now that we're trying to beat is 99%. And for 99%, what is the z-score that corresponds to 99% in problem number 26? Right, so we use so what is the z-score that corresponds to 99% confidence interval in number 26? Well, for 99, a confidence intervals of 99%, the z-value, which are later on called critical values, how we calculate that? Remember that what we do, we say that if there is 99% in between confidence, the tails, which are called the alpha, is 0.01, 1%, which is 0.01. Half of that is 0.005. And if you go to the negative table and you try to find out an area of 0.005, right here, even the values right here, it will tell you that the corresponding z-value is negative 2.575. That will be 2.575. So this is plus or minus 2.575. So that is the value that you're going to use here. But without calculating it, in this case, the margin of error is this value, square root. The sample size is 6,400, and the proportion in the sample is 920 divided by 6,400, which is 0.3. So Q is 0.7. Those numbers have to add up to 1. Actually, this is pretty easy to calculate, so let's do it. 0.3 times 0.7 divided by 6,400, and then we take the square root of that and multiply that number by 2.575, gives me a margin of error of 0.0147, which is this answer. Okay, so let's continue. All right, let's look at problem number 28. So in problem 28, it says that a survey, a survey of 865 voters in one state reveals that 408 favor an approval of an issue, right? And so, let me get a pen first. Okay. Construct a 95% confidence interval for the true proportion of all voters in the state who favor the approval. So what we are doing right here is this. We have a population right here, right? And we want to know what is the true proportion of members of the whole population who favor the issue right here, favor approval, right? So now what we are doing, since we cannot calculate this value, what we did is we took a sample, and the sample is a pretty large sample, 865 voters, okay? And we find out that in the sample, 408 favor the issue. So the proportion in the sample of those who favor is going to be 408 divided by 865. So let's calculate that number. This is the proportion in the sample. 408 divided by 865, which is equal to 0.472. All right, so the proportion in the sample who did not favor the issue is 1 minus 0.472, which is 0.528. 1 minus, which is equal 0.528. All right, so we have that. So now, so the way that we estimate the proportion of the population, instead of estimating and saying that it's probably similar to the proportion in the sample, which is a point estimator, we built an interval, and that interval is just taking the proportion in the sample, which is 0.472, and subtracting this magic number called the margin of error, 0.472, and adding the margin of error. So what is the margin of error? Is the z-value, which what this does is this create the range of numbers that is dependent on the level of confidence that you want to have. In this case, is 95. Square root of PQ over N. So for a 95 confidence interval, the z-value is 1.96. Some of those we start memorizing, so we don't have to look at the table every time. The proportion in the sample who favor is 4.472, and who doesn't favor is 0.528, divided by how many people were surveyed, which is 865. And all this inside the radical. So let's find out what this number is. We got 472 divided by 865, square root of this, times, okay, so 0.472 times 0.528 equals, divide this number by 865, and then we take the square root, then we multiply by 1.96, and we get that the error, the margin of error, is 0.0333. All right, so now we're ready to build the interval. So our interval is 0.472 minus the error, which is 0.0333, and it will give me, to 3 decimal places, 0.439. The upper limit is going to be 0.472 plus 0.033, which is 0.505. Okay, so we see the closest answer is going to be C. All right, very close. Very good. So let's move to the next problem. All right, so let's look at problem number 29. In problem 29, again, what do we want to do? What is the question? Is to construct a 98% confidence interval for the true proportion of a population. So we want to find the true proportion of a population is in between two numbers. Is the proportion in a sample minus the margin of error, the proportion in a sample plus the margin of error, right? So what is the proportion in the sample? Of 346 items tested, 12 are found to be defective. So the proportion of defective in the sample is going to be 12 out of 346. Let's find out what is the proportion in the sample that are defective. We hope it's not too many. It's not a large proportion. 346. That is 0.347. So that is the proportion in the sample that are defective, about 3.4%. The proportion in the samples that are not effective is 1 minus this number, which is 0.9653. All right, so we have these two numbers already. Now, so the proportion in the population with 98% confidence is between 0.0347 minus E and 0.0347 plus E. All right. So to complete this problem, all we need to do is calculate the margin of error, which is the z-score square root of p hat q hat over n. Now, what is the z-score? When we want to build a 98 confidence interval, that means that in the tails, what we call the alpha is 2%. That means that in half of a tail, let's say the left tail, we have 1%, which is 0.01. If we go to the negative table and try to look for an area of 0.01, let me see, let me make this bigger. Right here we have 0.099, the value will be 2.301234. Right here, 2.31234. So that would be 2.34. So the z value is 2.34. And then this is 0.0347 times 0.9653 over, what is sample size? 346. So E is equal to, all right, so what is P again? 0.0347 times, what is Q? 0.9653 equals, divided by 346 equals a square root of that, and then we multiply this by 2.34, and I get this number to be 0.023. After all these calculations, let's find the interval finally. All right, so we got this number, which is 0.0347 minus 0.023, and then 0.0347 plus 0.023. The lower limit is 0.0347 minus 0.0223. That gives me 0.0118. The upper limit is 0.0347 plus 0.023, which equal to 0.057, and this approximation is 7. Okay, so the closest. Now, why is that these answers, for example, it has 0.0576 and we have 0.0577? Again, The difference that we have is in the 1,000 location. Now this is the the tenth, the 100,000, the 10,000 location, and it is because the approximations that we do here in the radicals. So this answer is actually very precise. Okay, so let's move to the next problem. All right, in this case, it says that 293 employees selected randomly from one company, 10.24% of them commuted by carpooling. Construct a 90% confidence interval for the true percentage of all employees of the company who carpool. So let's do this with the decimal proportions because we're used to that, and then we convert that to percentages because otherwise we may get confused. So let's start right here. Of 290 employees selected randomly from, let me get a pen. Keep changing colors. Okay, so 290 employees selected randomly from one company, 10%. So that's the proportion who in the sample who carpool, 10%, that will be 0.1024, all right, of them commute by carpooling. Well, the ones who don't commute by carpooling is going to be 1 minus this number. So let's calculate that value. 1 minus 0.1024 gives me 0.8976. All right. So in constructing my interval, I'm going to say that the proportion of the population that carpools is probably between, with this degree of confidence, between 0.1024 minus the margin of error, 0.1024 plus the margin of error, right? So what is the margin of error? The margin of error is going to be the z-value times PQ over N. Well, what is the z-value that corresponds to 90% confidence interval? That would be 1.645 for 90% confidence, square root of 0.1024 times the Q, which is what happened to point? Oh, why when I press that it disappear? Okay, so let me do it down here. Oh, the program. All right, so right here we have the calculation. So the E is going to be the C value corresponding to 90%, which is 1.645, square root of P hat, the proportion in the sample, which is 1024, Q, which is 1 minus P, which is right here, 8976, divided by the sample size, which is 293. That's the people that we questions. This should give me 0.029. So that is the margin of error. So what I need to do is add this number. So we have 0.1024 minus 0.029 for the upper value, lower bound, which is 0.0733, and the upper value is 0.1024 plus 0.029, and that gives me 0.1024 plus 0.029, which gives me 0.1314. So we write these numbers as percentages. We multiply by 100, so we got 7.33% for the lower bound and 13.14% for the upper bound, which is this answer right here. Okay, good. Now let's look at this problem right here. Now, notice that in this particular problem, we are going to build a confidence interval from a sample. But in this particular problem, if you notice, we want to use the confidence level and sample data to find the confidence for estimating the true proportion, the true mean of the population. So right here we are estimating is the mean of a population, not the proportion. Okay, so before even begin, what that means, that we think that the true mean of the population, whatever population we're talking about here, is with some degree of confidence, in this case 98, is between a sample mean minus the error, a sample mean plus the error. So again, a point estimator would be to use just the sample mean to estimate the population proportion, the parameter. But a better estimate is to construct an interval. Okay? So now that we build this interval right here, the margin of error is different because it comes from the sampling distribution of sample proportions. It's the z-value, but in the sampling distribution for sample means, the standard deviation is the standard deviation of the population divided by the square root of the sample size. All right, so it may be even simpler. So notice that a random sample of 136 full-grown lobster. So we have a what is considered a large sample, 136. Have a mean weight of 22 ounces. So the mean of the sample is 22 ounces. And a standard deviation of 3.2 ounces. And so the standard deviation that is given, well, you're given the standard deviation of the sample, but we have a large sample, so let's assume that that is the standard deviation of the population. What is it? Is 3.2 ounces. Construct a 95% confidence interval, so your beta is 98%. And so we need to find the z-value that corresponds to 98%. How we do that? I think we have done this before, but I don't remember the value. So how we calculate that z-value? 98% is the tail is going to be 2% or 1%, 0.01. We go to the table for 0.01 is 2.30123, 2.33. So the z-value corresponding to 98 is 2.33. All right. So our interval is becoming simpler to compute. Is 22 minus e, 22 plus e. All right. Now, what is the margin of error? Right here we have the formula. So e is equal to the z-value 2.33 times standard deviation given, which is 3.2, divided by the sample size 136. Let's calculate this number. So 3 divided by times 2.33, I get a value of 0.6, right? 0.6. So we take this from 22, so get 21.4. 22.6. Since they're approximating to the next decimal, 21.4 to the rounding to the unit. So this will give me 21. All right. A 22 rounded up is 23. Okay, what answer is that? A. Okay, so right here we are estimating the population mean with an interval. We took a sample and we just built one interval. And we're confident that the mean of the population is there. How confident are we? 98%. This is a 98% confidence interval. We need to build more intervals in which we are 98% confidence to start narrowing what is the true population mean. But at least we have one right here. Okay, so let's do another example. All right, so right here we said that an amount of 73, that's kind of a large sample. So we took a sample of 73, and in this case from a population of chicken eggs, and found that the mean cholesterol level, so found that the mean in the sample, so we shouldn't use this notation because the notation that we use for sample mean is this one. The mean in the sample is equal to the amount of was 230, that's 230 milligrams. The standard deviation of the population is known from before, that's why it's sigma, given at the 17.4 milligrams. And we want to construct a 90% confidence interval to estimate the true mean of the population of X. So the true mean of the population is what? Is estimated from the sample mean to 30 minus the error, the sample mean plus the error. All right? So now what we want to do here is estimate the E. We have the formula for that. The margin of error is going to be the z-value times sigma square root of n. Right? What is the C? Well, for 95% confident, we don't know the z-value. We don't need to go and find it like we did for 98. It's 1.96. The standard deviation is 17.4 divided by the square root of the sample size, which is 73. So let's calculate this number. 17.4 times 1.96 divided by the square root of 73 got me to be 3. Basically I got 3.994. So we add this number, so we get 236 and 234. 226. 230 minus 4 is 226. All right, to 234. So that is an interval where we're confident we're going to find the population, the true mean cholesterol level for all X, right? So we're creating intervals here to estimate population means. Last problems we were estimating population proportions. Let's do the next problem. All right, so what we have right here is that a group of 64, so we selected a sample of 64. So the sample size is 64. Randomly selected, so you have a mean score. So the mean of the sample is what? 38.6. With a standard deviation of, notice that the standard deviation given is not of the sample of the population. We know that by the symbol of 4.9 on a placement test. What is the 90% confidence interval? So if we want to have a 95% confidence interval, the critical values for that are going to be 1.645 plus or minus, right? And so our interval is basically the mean of the sample minus the margin of error, the mean of the sample plus the margin of error. Okay, so now what is the margin of error in our case? So the margin of error is the z-value sigma square root of n. This gives me 1.645 4.9, which is the standard deviation, divided by the square root of the sample size, 64. So the square root of 64 is 8. So the E is equal to 4.9 times 1.645 divided by the square root of 64. And I got 1. All right. So, so the mean of the sample will be 37.6, and we add 1 to this, so that would be 39.6. So this is our interval. This is where we are confident we should find the population mean, that in this case is the average for all students who took this test. All right. We should construct more of these 90% intervals. And in 90% of them, we're going to find the true mean of the population. Okay, so in the last two problems that I'm going to solve here of this study guide, what we notice is so right here in these last two problems, one thing that we have to notice is this. So we are doing the same thing. We are trying to, if you notice, trying to construct a confidence interval for the population mean, right? So we already know that to, let's say, number 36, to build a confidence interval for the population mean, what we do is we relied on a sample mean to create an interval based on adding and subtracting the margin of error, all right? But the difference right here is that we have the mean of the sample, which is 12.7. So we have 12.7. We're going to subtract the margin of error, and we're going to add the margin of error to 12.7 to create the interval at the level of confidence that we want, plus the margin of error. What is different in this problem is that the sample size is small and we don't have the standard deviation of the population. If you notice right here, the sample size is only 10. Now, what do you think happens in an estimation when the sample size is too small? Well, small is convenient and it could be more cost effective to just test a medicine on 10 people than to test the medicine in 1,000 people. So small samples are very convenient. However, because you're using a small sample and it's small, and you don't have the standard deviation of the population, then what you need to do is use for the critical value in the error, you need to use what is called a t-value. So that value actually comes from what is called a t-distribution, which is a distribution that is also symmetric. It's like a normal distribution, but it really dependent on sample size. So that particular distribution for different sample size, it looks different. And it all depends on something called the degrees of freedom. So the margin of error is going to be equal to, instead of a z value, we're going to find a t value, times we don't have the standard deviation of the population, so we use the standard deviation of the sample, square root of the small sample size. Okay. In our case, standard deviation of the population is given as 3.7, and the sample size is only 10. So the only thing that we need is the t. So for that we use the t-table, and because we're creating a confidence interval, we always use two tails. So we calculate the degrees of freedom, which is n minus 1. In this case, is going to be 10 minus 1, which is 9. We calculate the alpha. Since the beta is 95, the alpha is 0.05. 95 is 0.95. 1 minus 0.95 is 0.05. Two tails. And this information is enough to find the t-value in the t-table. Let's go to our formula page. And now we go to the t-table. So like we did in the video, in the tutoring video, right here we have the two tails. We're looking for that number 0.05, which is right here. 0.05 and 9. And we got the value to be 2262. So the t-value is 2262. All right. Now what we do is we put that value. So the error is going to be 2.262 times 3.7 divided by the square root of 10. That gives me 2.262 times 3.7 equals divided by 10 square root, and I get 2.65. So I'm ready to build my interval. So it's going to be 12 minus 2.65, so 12.7 minus 2.65, and I get 10.05, less than the mean, less than 12.7 plus 2.65, 15.35. All right. See, we have an answer similar to that. 10.05, 15.35. Yep, we have this answer right here. Okay. Okay. So let's do the next one, number 37. So in problem 37, let me paste that problem here. We have. All right, so in problem 37 right here, all right, what do we have in problem 37? Again, we want to create a confidence interval to estimate the population mean. So every time we have to build a confidence interval, we usually are going to take a sample mean and we're going to add and subtract this margin of error to create a range of values where we are confident we can find the mean of the population, right? Now this is 99% confident. So we take the mean of the sample, which is 77.4. We're going to subtract the error, 77.4, and we're going to add the error, okay? What is the error again? Well, this sample size is small. It's only, well, the sample size is large, it's 1 or 2, but we don't have the mean of the population. We don't have the standard deviation of the population. Oh, we do have the standard deviation of the population. So that's good that this problem came here, because we can tell the difference between the two. This is a large sample, and the standard deviation of the population is given, so we can actually use a z value instead of a t value. So I didn't notice that, but look, the sample size is 1 or 2, and the standard deviation of the population is given as 6.5. And so since we can consider a 99% confidence interval, actually use the z-value, which we found before is 2.575 for 99. So that gives me the error to be 2.575 times 6.5 over the square root of this large sample size 102. That gives me, I can multiply the numerators first, the 2.575 times 6.5, and then divide that by the square root of 102, and that gives me 26. All right. Oh my gosh, that's large. Did I do this right? I probably did not do this right. That is not going to be 26. Let me get my eraser. So let's do it again. So we got 2.575 times 6.5 divided by 102 square root. Get 1.66. So the upper value is 77.4 minus 1.66. We get 75.74. All right, and the lower value, the upper value is 77.4 plus 1.66 gives me 79.06. Right, and so rounding to one decimal, which is what they have in the answer choices, this is 75.7, and this will be 79.1. Okay, so that's very good that we have this problem next to each other to tell the difference between when we have to use a z-value or like we did in this case, a t-value. Okay, so when do we use a t-value? When we have a small sample size and we don't have the standard deviation of the population like happens here. Small sample and the standard deviation of the sample. Right? All right, well, good luck. Thank you for paying attention.